Welcome back. In the previous lesson, we compared circuit switching with packet switching. We saw that the traditional telephone network, the PSTN, is the classic example of circuit switching. Today, we open the hood of that network and look at how it is actually built. PSTN stands for Public Switched Telephone Network. It is the worldwide collection of interconnected, voice-oriented public telephone networks. Although today most voice traffic rides on packet networks, the PSTN is still the textbook blueprint for understanding hierarchical, circuit-switched, narrowband communication. Every PSTN call begins and ends at customer premises equipment, called CPE. CPE is the gear sitting at the user side of the network: the telephone handset, the answering machine, the analog modem, the PBX in an office. From the CPE, a single twisted pair, called the local loop, runs all the way to the nearest end office of the telephone company. This local loop is typically a few hundred meters to a few kilometers long. It carries an analog voice signal that, inside the end office, is digitized into a 64 kilobit per second PCM channel. 64 kilobits per second is the fundamental currency of the PSTN. Everything above this layer is built by grouping these channels together. Now let us climb the hierarchy. The classical North American PSTN was organized into 5 levels of switching offices, called Class 1 through Class 5. Class 5 is at the bottom. It is the end office, also called the local exchange. This is the office that owns your local loop. Every subscriber line terminates here. A typical end office serves a few thousand to a few tens of thousands of subscribers. Class 4 is the toll center. It collects traffic from many end offices in the same area and switches inter-exchange calls. Class 3 is the primary center. It aggregates several toll centers and provides regional switching for long-distance calls. Class 2 is the sectional center. It interconnects primary centers across a wider area. Class 1 at the top is the regional center. There were only a handful of these in the entire country. Class 1 centers were fully meshed with each other to provide nationwide coverage. The traffic flows like a tree. A local call may stay entirely inside one Class 5 office. A call across town goes Class 5 up to Class 4 and back down. A long-distance call may climb several levels before coming back down on the far side. Each step up the hierarchy aggregates more traffic onto fewer, fatter trunks. Above the regional center sits the international gateway, which connects one country's PSTN to another country's PSTN through submarine cables or satellites. Modern networks have flattened this hierarchy, but the same logic still applies. Concentrate traffic, multiplex it, and switch it as high in the tree as needed. Inside this hierarchy, you will find 3 different kinds of nodes: switching nodes, transmission nodes, and service nodes. Switching nodes are the actual exchanges. Their job is to set up the path for each call. There are several flavors. The local exchange terminates subscriber loops and switches calls between local subscribers. The tandem exchange does no subscriber termination at all. It sits between local exchanges and forwards calls between them. The toll exchange handles intercity traffic, and the international gateway exchange is the door to other countries. Transmission nodes do not switch calls. Their job is to carry the aggregated traffic between switching offices on high-capacity trunks. These trunks were historically twisted pair, then coaxial cable, then microwave, and finally fiber optic. Inside the transmission node, you will find multiplexers, regenerators, and cross-connects that combine many 64 kilobit per second channels into the E-carrier or T-carrier hierarchy we will study in the next lesson. Service nodes are the brain of the network. They are the databases and signaling controllers that decide what to do with a call. They store routing tables, billing information, subscriber profiles, toll-free numbers, and number portability data. All three node types are tied together by a special signaling network called SS7, Signaling System Number 7. SS7 is out-of-band signaling. That means the signaling messages, dial digits, ring requests, busy tones, hang up, do not travel on the same channel as the voice. They travel on a separate packet network that connects all the switching offices. The endpoints of SS7 are called service switching points, or SSPs. SS7 packets are routed by signal transfer points, or STPs, and the databases I just mentioned are called service control points, or SCPs. Out-of-band signaling is what allows modern PSTN features like caller ID, call forwarding, three-way calling, and toll-free numbers. Let us work through a classic problem that shows why the hierarchy exists in the first place. Imagine a small region with 5 local exchanges. Call them A, B, C, D, and E. We want any subscriber on any exchange to be able to call any other subscriber. Approach 1. Full mesh. Connect every exchange directly to every other exchange. How many trunk groups do we need? Each exchange must connect to the other 4, but each connection is shared between 2 exchanges, so we count it once. The formula is n times n minus 1 divided by 2. For n equal to 5, that gives 5 times 4 divided by 2, which equals 10 trunk groups. Approach 2. Tandem. Place one tandem exchange in the middle and connect each local exchange to the tandem with a single trunk group. The tandem switches calls between any 2 locals. How many trunk groups now? Just 5, 1 per local exchange. Compare 10 trunks for full mesh versus 5 trunks for tandem. The tandem cuts the number of trunks in half. And as the network grows, the difference becomes much larger. With 10 exchanges, full mesh needs 45 trunk groups, but tandem needs only 10. With 100 exchanges, full mesh needs 4,950, while tandem needs only 100. Of course, tandem is not free. Every call now passes through one extra switch, which adds delay, equipment cost, and a single point of congestion. But the savings on trunk infrastructure are enormous, especially over long distances where the trunks themselves dominate the total cost. This is exactly why the PSTN hierarchy was invented, to push as much traffic as possible onto a small number of high-capacity, well-utilized trunks instead of a huge mesh of lightly used direct links. Let us summarize today's lesson. The PSTN is a hierarchical, circuit-switched, narrowband public network built around 64 kilobit per second voice channels. Every call starts at customer premises equipment and travels over a local loop to the nearest end office, also known as the Class 5 exchange. Above the end office sit 4 more levels in the classical hierarchy: toll center, primary center, sectional center, and regional center. Inside this hierarchy, 3 kinds of nodes work together: switching nodes that set up calls, transmission nodes that carry aggregated traffic on trunks, and service nodes that store routing and billing information. All of these nodes communicate over SS7, a separate out-of-band packet signaling network with SSPs, STPs, and SCPs. Our worked example showed why the hierarchy exists. A tandem switch dramatically reduces the number of trunks compared to a full mesh, especially as the network grows. In the next lesson, we will zoom in on the trunks themselves and study PDH, the plesiachronous digital hierarchy, which is how those 64 kilobit channels get bundled into the E1 and T1 carrier systems that ride between the offices.